Let's wrap up the example that we started in the previous video. So to remind you, we're trying to evaluate the integral over r of 4 times x plus y e to the x minus y, where r is this region in the xy plane. Here are the things we found out. Using the substitution from the last video, dA, in other words dx dy, became 1/2 du dv. The integrand 4 times x plus y e to the x minus y became 4u e to the v, and S was the region in the UV plane corresponding to this region R, where S is bounded by the coordinate axes and the curve u minus v equals 2. So let's put it together. The double integral over R of 4 times x plus y e to the x minus y dA becomes the double integral over S of 4u e to the v times 1/2 du dv. Of course, we can cancel the 4 with the 2 to get a 2. So we have 2u e to the v, and then du dv in some order. So now let's see if we can set up our bounds. This region S is both vertically simple and horizontally simple. So I could set up the bounds either slicing vertically or horizontally. Notice if I slice vertically, then I'm going to be going from the curve to v equals 0, which means that v equals 0 is going to be my upper limit of integration. But if I slice horizontally, then I'll be integrating from u equals 0 over to the line, which means that u equals 0 is equal to the lower bound of integration. And I just kind of like it better having the zeros on the bottom. So that's the only reason that I'm going to choose to slice horizontally rather than vertically. So I need to write both of these curves in the form u equals. This one already is, it's u equals 0. Let's rewrite this curve as u equals v plus 2. So u is going to go from 0 to v plus 2. So when I set up the bounds, on the inside, I have u going from 0 to v plus 2. And on the outside, v takes on its smallest value of -2 and the biggest value of 0. So my bounds with respect to v are from -2 to 0. And now that we have the integral set up, I can erase everything over here to the right and just work on carrying out the integral. You might ask yourself quickly whether we could do this using the shortcut, since notice that the function inside can be factored as a function of u multiplied by a function of v. But notice that we're not integrating over a rectangle. In fact, we just saw we're integrating over a triangle. Not all 4 bounds are constants. So let's just start by integrating this part with respect to u, treating the v's as constants. Well, the e to the v will be a constant, and the integral of 2u is u squared. So I have u squared e to the v, taken from v equals 0, from u equals 0, to u equals v plus 2. And now I'll plug in the 2 endpoints for u and subtract. First, plugging in u equals v plus 2, I get v plus 2 squared e to the v minus, when I plug in u equals 0, I get 0. Now I need to do that integral. Well, here I see that I have a polynomial times an exponential. So I think that using integration by parts is called for. Since the polynomial has degree 2, I'll have to use integration by parts twice. So maybe a more efficient way of doing it would be to use tabular integration as a shortcut. So over here, I'll put the function that I'm going to differentiate, which is the v plus 2 squared. And over here, I put the other part that I integrate, e to the v. So I'm going to differentiate this until it disappears and integrate this the same number of times. So the first derivative is twice v plus 2 to the first times 1. The second derivative is just 2, and the third derivative is 0. Integrating e to the v the same number of times, I have e to the v, e to the v, e to the v. And then remember, we take products along diagonals and alternate signs. And that'll give me my antiderivative. So the antiderivative here will be v plus 2 squared e to the v minus 2 v plus 2 e to the v plus 2 e to the v. And all of that will be taken from negative 2 to 0. So I need to plug in the 0 first, and then the negative 2, and subtract. So first of all, let's plug in v equals 0 into all of this. That'll give me 4 e to the 0 minus, I'm plugging in v equals 0, so that's another 4 e to the 0 plus 2 e to the 0 minus, now I have to go through and plug in v equals negative 2. Well, this is nice. Negative 2 plus 2 is 0, so I have 0 times e to the v minus, plugging in v equals negative 2, I get another 0 e to the v plus, this term doesn't disappear. I get 2 e to the negative 2. So simplifying a bit more will be done. 4e to the 0 minus 4e to the 0 is 0. E to the 0 is 1, so that term simplifies to just 2 minus 2e to the negative 2. And that's the value of the integral.